I was standing in a muddy field outside Bastogne in January 1945, staring at a Tiger tank that had been abandoned without a scratch on its armor. The crew had simply walked away. My maintenance officers were baffled. The transmission had seized solid, but there were no bullet holes, no shrapnel damage, nothing that explained why 45 tons of German engineering had become a paperweight in the middle of a retreat. This wasn't the first time. Since crossing into Germany, my Third Army had been finding perfectly good German equipment abandoned for mechanical failures that made no sense. Panzer engines seizing after 200 hours instead of 800. Half-tracks breaking down every 50 miles. Even their damn bicycles were falling apart faster than they should have. My intelligence officers started asking questions. What we discovered changed how I understood the entire war. The answer came from a Swedish metallurgist named Erik Lundberg, working for SKF Ball Bearings in Gothenburg. In March 1941, 2 years before we figured any of this out, Lundberg had identified a flaw in German steel hardening that was so subtle it took electron microscopy to detect. The Germans were using a chromium-molybdenum alloy that looked perfect on paper but had a crystalline structure that degraded under sustained heat cycling. Every ball bearing coming out of Schweinfurt had this defect. Not some of them, all of them. German quality control never caught it because their testing methods were designed for peacetime use. They would run bearings for 100 hours and call them good. Lundberg's analysis showed the failure point came at exactly 60% of rated lifespan, which meant German bearings started failing after 6 months of war conditions instead of the promised 12. The Wehrmacht was grinding itself to death, literally. I started tracking the timeline. In 1941, German tank divisions were covering 300 miles in a week during Barbarossa. By 1943, the same units were lucky to manage 100 miles before half their vehicles broke down. German pilots were reporting engine failures at twice the expected rate. U-boat crews were surfacing in the middle of combat because their electric motors burned out. The real beauty of it was that nobody in the German command structure understood what was happening. Their field reports kept blaming combat damage, poor maintenance, or sabotage. They never connected the dots because the failures looked random. A transmission here, an engine there, electrical systems failing for no apparent reason. But it wasn't random. It was physics. Schweinfurt was producing 12 million bearings per month by late 1943. But 60% of them were essentially time bombs. German factories had to rebuild tank transmissions every 3 months instead of every year. Aircraft engines were being scrapped after 200 flight hours instead of 500. The numbers tell the story better than any propaganda. In 1942, German tank production peaked at 1,500 units per month. By 1944, they were building 2,000 tanks per month but losing 1,800 to mechanical failures before they reached the front lines. They were literally building tanks faster than their own bearings could keep them running. I saw the evidence firsthand during the Ardennes offensive. German armor that should have punched through our lines was stuck on the side of roads with seized transmissions. Panzer divisions that started the battle with 120 operational tanks were down to 40 tanks after 3 days. Not from combat losses, but from mechanical breakdowns. One particular incident stuck with me. December 18, 1944, near Houffalize. An entire company of Panzerabwehrs had been abandoned in formation, engines still warm, fuel tanks full. Not a single round had been fired at them. The lead tank's final drive had seized, blocking the road. The second tank's transmission locked up trying to push it aside. The third tank's engine threw a rod when the bearings disintegrated. Within 2 hours, 16 tanks were immobilized by cascading mechanical failures. The crews stripped the machine guns and radios, then walked back to German lines. 40 years of German engineering superiority undone by microscopic flaws in steel crystal structure. The Swedish engineers' report had been shared with British intelligence in 1941, but nobody understood its strategic significance until 1943. By then, German industry had produced over 50 million defective bearings and installed them in everything from Messerschmitt fighters to Tiger tanks to U-boat periscopes. What made this particularly devastating was the replacement timeline. Even if German engineers had identified the problem immediately, Fixing it would have required rebuilding their entire metallurgical process and replacing every bearing in service. With Allied bombing campaigns targeting Schweinfurt specifically, they never got the chance. I watched German tank crews in Normandy abandon perfectly good Panthers because the final drive bearings had welded themselves solid. These weren't rookies or cowards. They were experienced panzer crews walking away from 70-ton tanks because German metallurgy had failed them. The psychological impact was almost worse than the mechanical one. German mechanics started losing confidence in their equipment. Pilots began aborting missions when they heard unusual engine noises. Tank crews started carrying extra oil and spare parts for repairs that shouldn't have been necessary. An army that had conquered most of Europe was developing mechanical anxiety. The failure pattern was predictable once you understood the metallurgy. Ball bearings would operate normally for 4 to 6 months, then begin generating excessive heat as the steel structure degraded. The heat would accelerate the degradation, creating a feedback loop that ended with catastrophic failure within days. By 1944, German logistics officers were calculating that every armored division needed 40% more spare parts than doctrinal requirements suggested. They were stripping components from disabled vehicles just to keep half their remaining equipment operational. Maintenance units that should have been performing routine service were doing complete rebuilds every few months. The Luftwaffe suffered even worse. Aircraft engines operating at high RPM and extreme temperatures failed faster than ground equipment. German pilots reported that BMW 801 radial engines were lasting 200 flight hours instead of the promised 500. Daimler-Benz VT-12s and Messerschmitt fighters were seizing up during combat, forcing pilots to crash land behind their own lines. Lieutenant Colonel Hans Rudel, their most decorated Stuka pilot, lost 3 aircraft to engine failures in 1944 alone. Each time, he reported hearing grinding noises from the engine compartment minutes before complete seizure. Rudel survived because he was skilled enough to dead-stick damaged aircraft back to friendly airfields, but hundreds of other German pilots weren't so lucky. Major Erich Hartmann, the highest-scoring fighter ace in history, recorded 14 forced landings due to engine failures between 1943 and 1945. His maintenance log showed consistent bearing-related problems in Messerschmitt Bf 109 engines. Hartmann learned to recognize the early warning signs and would immediately head for the nearest airfield when he heard unusual engine vibrations. U-boat crews faced the most dangerous consequences. Electric motor failures while submerged meant emergency surfacing in hostile waters. Between 1943 and 1944, 17 German submarines were lost due to mechanical failures that forced them to surface within range of Allied aircraft or warships. U-511 surfaced off Gibraltar in August 1943 because both electric motors seized simultaneously. British destroyers were on top of them in 12 minutes. U-628 had to surface during a convoy attack when bearing failures caused electrical fires in the motor compartment. RAF Coastal Command Liberators sank her 30 minutes later. Captain Heinrich Lehmann-Willenbrock, commanding U-256, reported bearing failures in his electric motors during 3 separate patrols in 1944. Each failure forced emergency surfacing procedures that nearly resulted in the loss of his boat. German naval records show that submarine availability rates dropped from 87% in 1942 to 41% by late 1944, primarily due to propulsion system failures. The irony was perfect. German engineering had a reputation for precision and reliability that went back decades. Mercedes-Benz, BMW, Krupp Steel, Zeiss Optics. These companies had built their reputations on quality that other nations couldn't match, but the pressure to mass-produce war materials had forced them to cut corners in ways that invalidated their entire quality control system. Each bearing failure created cascading problems throughout German supply chains. A seized transmission didn't just disable one tank. It required a recovery vehicle, replacement parts, specialized mechanics, and often a complete engine rebuild. Multiply that by thousands of vehicles failing simultaneously, and entire divisions became logistical nightmares. Colonel Heinz Guderian, commanding the 2nd Panzer Army in 1944, was reporting mechanical availability rates of 43% by September. For every 100 tanks in his order of battle, only 43 were operational at any given time. The rest were either broken down, being repaired, or awaiting parts that didn't exist. German tank recovery units were working around the clock. Each heavy recovery vehicle was servicing 15 disabled tanks per week instead of the planned 3. Recovery crews were cannibalizing 2 or 3 broken tanks to get one running, creating maintenance graveyards across the German front lines. Stories like this disappear from history unless someone preserves them, so make sure you don't lose this channel. The 12th SS Panzer Division Hitlerjugend started the Normandy campaign with 150 tanks. By July 20th, they had 12 operational vehicles. Combat losses accounted for 38 tanks. The remaining 100 had been abandoned due to mechanical failures, primarily transmission and final drive problems caused by bearing degradation. I met Erich Lundberg after the war ended. Quiet man, thick glasses, hands that shook when he talked about what his discovery had meant. He told me he had tried to warn German colleagues in 1941, before Sweden's position in the war became clear. Professional courtesy, he called it. His letters never reached anyone who mattered. Lundberg showed me his original analysis. The chromium-molybdenum alloy formed carbide precipitates under thermal stress, creating microscopic fractures in the bearing races. These fractures propagated until the bearing surface became rough enough to generate heat, which accelerated the carbide formation, which created more fractures. The chemistry was elegant in its destructiveness. At temperatures above 180 degrees Celsius, which every tank transmission reached during combat operations, the carbide particles would migrate to the grain boundaries in the steel matrix. This migration created stress concentrations that initiated fatigue cracks propagating at predictable rates. Lundberg had calculated the exact failure timeline based on temperature and load cycles. Bearings operating at 200 degrees under combat conditions would last exactly 147 days before catastrophic failure. German quality control had tested bearings at 150 degrees under light loads and assumed they would last twice as long in service. The Swedish engineer had tried to publish his findings in the Journal of Applied Metallurgy in 1941, but wartime censorship prevented distribution to German scientists. British intelligence obtained copies through neutral Swedish contacts and filed the report without understanding its strategic implications. German metallurgists had chosen the alloy because it was 30% cheaper than alternatives and could be produced in existing furnaces without retooling. They had tested it extensively, but their test protocols simulated peacetime industrial use, not the extreme conditions of mechanized warfare. The decision to use this steel had been made in 1940, when Germany expected a short war against divided enemies. By 1943, when the bearing crisis became apparent, Germany was fighting a global conflict on multiple fronts with no time or resources to fix fundamental metallurgical problems. Dr. Ferdinand Porsche, designing the Tiger II tank in 1943, specifically requested high-grade Swedish steel bearings for the final drive. German procurement officers denied the request, citing strategic material shortages. Every Tiger II produced used Schweinfurt bearings with the metallurgical defect. The result was predictable. Tiger II tanks had an operational readiness rate of 28% by early 1945, not because they were being destroyed in combat, but because the final drives kept failing. These were the most heavily armored, most powerful tanks Germany ever produced, and they couldn't stay running long enough to matter strategically. Heavy Tank Battalion 503, equipped with Tiger IIs, reported to Army Group Center in January 1945 with 45 tanks. Within 2 weeks, 31 had been abandoned due to final drive failures. The remaining 14 tanks were immobilized, awaiting replacement parts that would never arrive. The bearing crisis affected equipment in ways that no one had anticipated. German radar sets used precision bearings in their rotating antenna assemblies. When these failed, entire early warning networks went dark. Flak gun directors relied on ball bearings for smooth tracking. Seized bearings meant anti-aircraft guns that couldn't track Allied bombers. Würzburg radar installations defending the Ruhr industrial area began failing systematically in late 1943. The rotating antenna assemblies seized up after 4 to 6 months of operation, leaving massive gaps in German air defense coverage. Allied bomber crews reported significantly reduced flak accuracy over targets that had been heavily defended just months earlier. Even German locomotives were affected. The Reich's rail system depended on millions of wheel bearings, axle bearings, and drive mechanism bearings. By 1944, German trains were breaking down every 200 miles instead of every 800. This paralyzed military supply lines more effectively than strategic bombing. Reichsbahn statistics showed locomotive availability dropping from 89% in 1942 to 37% by 1944. Each locomotive failure caused cascading delays throughout the rail network. Military supply trains that should have reached the front in 18 hours were taking 4 days, often arriving to find the units they were supplying had already retreated. Field Marshal Erwin Rommel's final inspection reports from Normandy in June 1944 mentioned mechanical reliability as his primary concern. His Atlantic Wall divisions had 37% of their vehicles in repair status, not battle damage. Mechanical failures that maintenance crews couldn't fix because replacement bearings failed just as quickly as the originals. The 21st Panzer Division, defending Caen, reported that their Panzer IV tanks were averaging 12 hours of operation between bearing failures. Tank commanders were ordering engine shutdowns every 2 hours to prevent overheating, which made coordinated attacks impossible. The final accounting was staggering. Conservative estimates suggest that bearing failures caused the premature loss of over 20,000 German vehicles, 4,000 aircraft, and 200 submarines. Not destroyed in combat, just broken down and abandoned because the machinery wouldn't work anymore. But the real impact wasn't the equipment losses, it was the strategic paralysis. German commanders couldn't plan offensive operations when they knew 30% of their tanks wouldn't reach the objective due to mechanical failures. Luftwaffe squadron leaders were grounding aircraft preemptively rather than risk engine failures during combat. Field Marshal Guderian's memoirs mention mechanical reliability as a constant concern after 1943, but he never understood the root cause. His panzer units were reporting 50% mechanical failure rates during extended operations, forcing him to keep enormous reserves just to maintain effective strength. Albert Speer, as armaments minister, commissioned a full investigation of German mechanical reliability in March 1944. The investigation team included representatives from BMW, Mercedes-Benz, Krupp, and the Schweinfurt bearing works. Their report identified bearing quality as the primary factor in equipment failures, but offered no solutions that could be implemented during wartime. Speer's team calculated that fixing the bearing problem would require 6 months of production downtime, complete retooling of steel furnaces, and imports of Swedish raw materials that were no longer available. The investigation concluded that Germany had no choice but to continue using defective bearings until the war ended. The investigation revealed that German industry had been aware of bearing quality issues since late 1942, but had suppressed the information to avoid production delays. Internal memos from Schweinfurt showed that quality control engineers had identified the metallurgical defect, but were overruled by production managers under pressure to meet armament quotas. German attempts to work around the bearing crisis led to increasingly desperate measures. Tank crews were ordered to shut down engines every 2 hours during road marches to prevent overheating. Aircraft mechanics were pulling engines after 100 flight hours for bearing replacement, whether they needed it or not. The Waffen-SS, with priority access to the best equipment, still couldn't escape the bearing crisis. The 1st SS Panzer Division had 87 tanks operational on D-Day. By June 15th, only 31 tanks were running. Combat losses accounted for 12 tanks. Mechanical failures had eliminated 44. SS Oberfuhrer Wilhelm Mohnke, commanding the 1st SS Panzer Division, sent increasingly desperate reports to SS headquarters requesting replacement parts and maintenance support. His final report in July 1944 stated that his division was combat ineffective due to mechanical failures, not enemy action. I saw this firsthand during my pursuit across France. German tank columns would start moving at dawn with 50 vehicles. By noon, 15 would be broken down on the roadside. By evening, another 20 would have seized up or thrown tracks. The remaining 15 tanks would arrive at their destination, having lost 2/3 of their strength to mechanical attrition. The 2nd Panzer Division, retreating from Normandy in August 1944, abandoned over 100 vehicles along a 60-mile stretch of road. My intelligence officers examined the vehicles and found that 87 had been abandoned due to mechanical failures, not fuel shortages or combat damage. German units began incorporating mechanical failure rates into their tactical planning. The 9th Panzer Division calculated that any operation lasting more than 72 hours would result in 50% mechanical losses. Operations were planned, assuming that half the equipment would break down before reaching combat. The Wehrmacht had spent 5 years building the most mechanized military force in human history, and it was being defeated by metallurgical chemistry that they couldn't see, couldn't predict, and couldn't fix. All because one Swedish engineer had understood something about crystal structures that German quality control had missed. German industry produced over 90 million defective bearings between 1940 and 1945. Each bearing was a metallurgical time bomb, guaranteed to fail at the worst possible moment. The cumulative effect was systematic paralysis of German military effectiveness across every theater of operations. Allied intelligence began exploiting German mechanical vulnerability by targeting repair facilities and spare parts depots. Bombing raids that destroyed bearing stockpiles had more strategic impact than raids that destroyed tanks, because destroyed tanks could be replaced, but failed bearings could not. The bearing crisis affected German industry beyond military production. Civilian machinery began failing at accelerated rates as war production consumed higher-grade materials. German factories were cannibalizing civilian equipment to keep military production lines running. By 1945, German machine tool production had dropped to 20% of 1942 levels, primarily due to bearing failures in manufacturing equipment. The industrial base that had supported German war production was collapsing from within, crippled by the same metallurgical defects that were destroying military equipment. Erich Lundberg's post-war analysis estimated that the bearing crisis reduced German military effectiveness by 35% between 1943 and 1945. This reduction was equivalent to removing 15 divisions from German order of battle permanently without firing a single shot. The bearing crisis lasted until Germany surrendered. Even in April 1945, we were finding abandoned German equipment with notes from crews explaining that the machinery had simply stopped working. No enemy action, no battle damage, just steel wearing out faster than anyone had calculated. That Tiger tank outside Bastogne never moved again. We pushed it off the road with a bulldozer and used it for target practice. 45 tons of German engineering reduced to scrap metal because someone in Schweinfurt hadn't understood how chromium-molybdenum alloys behave under sustained thermal stress. Wars are won by logistics, and logistics depend on machinery that works when you need it. The Germans learned this lesson too late to matter. Stories of technical failures like this shaped the entire conflict, but they get buried under narratives about heroism and strategy. Subscribe now, because military history's most important lessons are always the ones that disappear first.